During 2020, GeoSolutions has participated to the OGC TestBed16, implementing a GeoPackage Server component. The objective was to advance the GeoPackage standard in terms of content discovery and ability to support large vector datasets. GeoSolutions used GeoServer, improving the existing GeoPackage support to sustain the TestBed16 goals. The server has also been used to publish the generated geopackages in order to verify their performance characteristics. In accordance to the testbed requirements, all code changes have been made open source. In particular, they have been contributed back to GeoTools for the package reading and production side, and GeoServer for the WPS machinery driving the process. First off, let's consider the improvements to contents discovery. Before TestBed16, GeoTools and GeoServer could only export the data. The work in TestBed16 allowed to export more information, such as dataset metadata, dataset provenance, styles, and common operational pictures. The work required adding support for previously unsupported extensions, such as metadata, portrayal, and semantic annotations. GeoServer can link to external metadata for each layer. When exporting the layer, the metadata is downloaded and embedded in the GeoPackage. This creates a new metadata table entry, including the text of the metadata sheet. Each contents table is then linked to the metadata via the metadata reference table. Access to the original data might be important for later updates. For this reason, the GeoPackage contains an OWS context pointing back to the WFS, where the data can be downloaded again. This metadata entry is tagged as dataset provenance via semantic annotations. Similarly, it might be important to run the same WPS export process again at a later date. To support this, another OWS context is added among the metadata, including a reference to the original WPS server and the full WPS execute request used to generate the GeoPackage. The portrayal extension is used to export all styles associated to the exported layers. Each layer can be associated to multiple styles. Each style is included in the output. Each style can have one or more style sheets associated with it. Each style sheet is the definition of the style in a different style language, such as SLD or Mapbox.gl styles. Finally, each style is associated to one or more content tables via semantic annotations. In this case, the same semantic annotation is tagging both the style and the content table, generating the association. Map symbols used in the server are also included in the generated GeoPackage. This makes the style in the GeoPackage fully self-contained. Given a multi-layer GeoPackage with styles, it's useful to know the preferred stacking order of the layers and which styles should be used for which layer. In GeoServer, this function is served by the layer group construct. During GeoPackage export, layer groups are exported as OWS contexts and stored in the metadata table. The same set of layers might be included in multiple layer groups, such as one for day view and one for night view. In this case, multiple definitions are exported. These OWS contexts are stored in the GeoPackage metadata and tagged via semantic annotations as common operational pictures. Let's now consider writing large vector GeoPackages. The first dataset used to test large GeoPackage exports is master map topography, kindly provided by Ordnance Survey. Master map is a large dataset, delivered as 50 GB worth of compressed GML files, and inflating up to 300 GB when imported in PostGIS. The database contains 6 tables with a grand total of almost 500 million rows. The dataset is very detailed and meant to be displayed at around 1 to 4000. Several attributes are enumerated. Also, Several have a multiplicity greater than 1 and are represented as arrays of values. In order to reduce the size of the GeoPackage, enumerated attributes have been represented as integers, using the core schema extension to associate each number to a value. In this example, the accuracy of position values are represented as integers. The field is, however, associated to a constraint in the data column table. The constraint provides human-readable values for each of the numbers. SQLite is commonly built with the JSON1 extension, allowing to handle text fields as JSON objects. Master map arrays have then been saved as JSON strings, and if enumerated, compressed again using numbers that the client can look up in the constraints table. It's interesting to see how this leads to size reductions. When converted to GeoPackage, the original database is already reduced down to around 250 GB. This is due to SQLite more compact disk representation. However, when using enumerations, the size is further reduced, down to around 200 GB. Despite this size reduction, the package is still very large. When drawing maps at 1 to 4000, the client is required to quickly locate a small amount of records out of the 500 million contained in the package. Following the PostGIS lead, we experimented with sorting records by geohash on insertion, trying to achieve a better physical file layout. Sorting by geohash leads geometries that are close on the map to be close on the disk as well. This is particularly beneficial for spinning disk storage, as it reduces seek time. However, it's also beneficial for modern SSDs, as it also reduces the amount of disk blocks that need to be read, improving the efficiency of the operating system file cache at the same time. In order to confirm this, we ran WMS load test against SSD storage, using an increasing number of concurrent clients. The test shows a significant speed increase when using geohash sorted packages, which is especially evident when the file system cache is empty at the beginning of the test. We also explored a different approach to handle large geopackages, in particular partitioning. The large package has been split in smaller geopackages using the 100 km UK grid as a reference. An index geopackage has then been created, which contains all the metadata and links to the smaller parts. This helps the client, as he can quickly locate the packages needed to build a map, ignoring the others. In particular, a table of parts is generated for each content table. This table of parts links only to the files that hold data for the layer in question. The list might be different layer by layer. The parts generated over the regular grid have significant different sizes, ranging from few kilobytes to 25 gigabytes. A different approach could be used instead, that uses an irregular space partitioning to create parts of similar size. The ZoomStack dataset has also been used for tests. ZoomStack is a freely available dataset provided by Ordnance Survey. Delivered as a 10 GB GeoPackage, it contains several layers and provides a multi-scale view of the United Kingdom. When zoomed out, only a small part of the data is shown in the maps. Locating this subset of data can be sped up using indexes. However, on large datasets, indexes alone are not enough, and performance suffers. A common approach, used often when rendering OpenStreetMap, is to create generalized tables. Generalized tables help performance in two ways. First, they contain generalized geometries. Second, and more important, they only contain records that are meant to be displayed at the target scale. Multiple generalized tables can be set up for each base table, targeting different scale ranges. If set up properly, this can lead to a significant speedup. During the testbed, we measured improvements up to 300 times on selected tables. Let's wrap up with some general notes about performance over large geopackages. During the testbed, we generated a number of very large GeoPackages. GeoPackages are SQLite databases, so common approaches to improve write performance have been used, including opening the database in exclusive access mode, disabling the transactional journal for the one-off production task, and using prepare statements and batches of inserts. During the testbed, we found that creation of spatial indexes takes a significant portion of the GeoPackage production time, especially for large files. In order to improve that, the R3 support in SQLite would need to be optimized. Also, sorting data by geohash requires writing the data twice, first to extract the original data and compute the hashes, and then another time to write the output package in the desired order. This has proven useful, but should be attempted only if the package is read many times after the export. Finally, while enums provide side benefits and are part of the core specification, their support is not widespread. It would help to get better support in common GIS libraries, such as GDAL. Thanks for watching. If you'd like to get more details about this activity, please look up and read the OGC TestBed16 GeoPackage Engineering report on the OGC website.